This mission distinguishes itself by being the first to drill really well underneath the surface of Mars, up to 2 meters underneath the surface. So with the PanCam instrument, we're seeing the broad scene, the rocks on Mars, looking for outcrops and looking for potential interesting sites to drill. So then the drill goes under the surface, gets the rocks from under the surface, and the Raman is one of the instruments which is looking at the rocks under the surface. So the powerful combination which we have is the visual and near-infrared imagery from PanCam, and then the spectroscopy from the Raman team. So it's a really powerful combination to work together.
Raman spectroscopy as an analytical technique has become extremely popular over the last decade or so, now that small portable devices are practical. It's used for measuring pharmaceuticals, it's used in security applications, and it can be used in forensic crime scene analysis as well. For Mars, it's going to be the first time an instrument like this has ever been deployed, and it's particularly important because it's sensitive to the molecular composition of materials. It's a non-destructive technique, so you can operate it multiple times without damaging the materials that you're interested in looking at, and it simply uses a laser to illuminate the surface of the sample, and you collect the light that comes back off it, and by looking at the fingerprint that's produced, you can identify the specific molecules that can give you information not just on the geology of the samples that you've got, but also on potential organic signatures as well.
Today we've been testing the ExoMars instruments, PanCam and the Raman spectrometer on this field site here, which is actually an old mine site. And this site has got a whole wide variety of different types of rocks and different types of minerals, which we can actually test our instruments on. So if we look at some of the rock types around here, for example, so this is a hydrothermal mineral vein that was deposited within a hydrothermal environment. And we have lots of different minerals in here, including calcite, which is this bright white one here, and also quartz, the slightly darker grey one. And these are minerals which are deposited in a hydrothermal system. And this is very important for Mars because hydrothermal environments have existed on Mars in the past. And we know from the same sorts of environments on Earth that these are inhabited by a wide variety of sort of extremophile microbial life. So exactly the kind of life that we're trying to look for with the ExoMars mission. Matt's imaging some rocks at the moment with the PanCam instrument system, and he's imaging a slightly different type of rock. This rock is called a shale. So this is a very fine-grained, clay-rich rock, which also formed in an environment which is very conducive to microbial life. So this is a very calm, sort of very aqueous environment, very water-rich. The sort of habitable environment on Mars that we want to be able to identify with the ExoMars instrumentation so we can look for signs of life within this geological rock record.
Coming to places like this enables us to have trial runs and to investigate different modes of operation, different types of acquisition processes, so that you can get the very best out of the instrument. It can be extremely tricky when the instruments you're trying to operate are so far away to understand how they're going to respond to the different types of material you find. So we're only going to have a few opportunities to get the information we want, and it's really important that it's right from the very beginning.
These field trips are really important, whether you're an engineer working on the actual instrumentation itself, or perhaps whether you're a geologist actually working on the data and interpreting the data sets that you get from these instruments. As a scientist, that's really important to know how much you can actually extrapolate and interpret something. The area that we're working at the moment is a really good geological analogue for the terrains that the ExoMars rover will explore, primarily because it's a type of sedimentary rock which has already been identified on Mars.
You can regard this basin in between as being analogous to a large meteorite impact crater on Mars, where the impact has excavated deep down and thrown these really ancient rocks up to the surface and gives us a chance of sampling into them that we wouldn't otherwise have.
You have so many different instruments and so many different people of different scientific expertise working on these missions. It's a really important thing to have this communication between all the different members of the mission.
With a camera going to Mars, one has to be particularly careful about temperature. At night, it gets down to minus 100 degrees centigrade, possibly even a minus 120. So you've got to test the instrument to make sure it's going to work over that wide temperature range. Also on the surface of Mars, because the atmosphere is relatively thin, there's a radiation environment which is higher than we have on the surface of the Earth and even higher than we have at the top of the atmosphere. Also, because the atmospheric pressure is low, it has to work in that environment as well. But probably the biggest challenge is temperature. That type of thermal flexing in our real optical bench going to Mars, that is certainly a challenge.
The ExoMars PanCam instrument has been under development now for a number of years, but it's not actually going to be a fully functioning prototype for a little while yet, because it's such a long development time. So in order to allow us to capture test data in the meantime, we've built this emulator system. So it's representative of the PanCam instrument, although not physically the same. So this is built with off-the-shelf commercial components, so standard off-the-shelf cameras and lenses. But we've also manufactured these filter wheels on the front, which give it the multispectral capabilities. So we have 2 wide-angle cameras mounted either end of the optical bench, and a high-resolution camera mounted just off to one side. It's absolutely critical now that we understand exactly what the camera's capable of. We're reaching the point where it's going to be too late to make any changes, so we really have to refine all the last details now. So all these field tests are critical for learning, more often than not, what we've done wrong in the past and how to fix it before it gets too late.